Okay, on this video we are going to talk about a method to convert a non-exact differential equation into an exact differential equation. Alright? It's a method that not always works, but you can try it. And that happens when you have the shape of the exact differential equation, but the cross partial derivative is not equal. So that means that it is not exact differential equation. However, somebody found a method to make it exact. All right. The way to do it is that he or she, I don't remember, is that he assumed that there was an integrand factor w of two variables, w of x and y, that you multiply times that the differential equation, and then it makes it exact. Now, what is the w of x comma y? We don't know it. We are going to develop the formulas to find w of x comma y. All right. So please pay attention, very careful. This is a demonstration because it's a long demonstration. I may not have enough space, so I'm going to write small. All right. Okay, so let's do this. Let's multiply these times the differential equation. So it's going to be something like this. I'm going to avoid the x comma y and x comma y. All right, just for the sake of saving space. So it's going to be w times m differential of x plus w times n differential of y equal to this times 0 is still 0. Now remember that w is a function of two variables as well as m and n. And just avoid writing this just to save space because the whiteboard is small. Okay, so what happens here is that this has changed and this is my m star. And this is not the same, it's an n star, it's just different, alright? Now, according to the theory, if that integrand factor is good, then what will happen is that the partial of the m respect to y, now it is equal to the partial of n star respect to x, which it was not equal in the previous, but now the m has the w times m and the new n star is w times n. Alright, now let's check if this happens. Alright, so taking the partial of m star respect to y, all that is equal to the partial respect to y of this multiplication, w times m. Alright, so let's do the development of this partial derivative. So because we have a multiplication is w times the partial of m respect to y plus m partial of w respect to y. Okay, so that is the partial of m star respect to y. Now let's do the partial of n star. I'm going to do it here. The partial of n star respect to x, so that is the partial respect to x of n star, and n star is w times n. Remember that w and the n and the m are functions of two variables. Alright, so it's going to be, because we have a multiplication, it's going to be w partial of n respect to x plus n partial of w respect to x. Now they are supposed to be equal, so this is supposed to be equal to that. Okay, so let's write it. W partial of m respect to y plus m partial of w respect to y equal to w partial of n respect to x plus n partial of w respect to x. Okay, remember, what are we looking for? The m is given, the n is given. What we don't know is the w of x comma y. Now from here, I don't see how can we calculate w of x comma y. So let's do one assumption. Okay, let's assume, because this is a very difficult problem, because this is a differential equation, but this is a partial differential equation. And we don't know how to solve partial differential equations. We know how to solve normal derivatives, normal ordinary differential equations. So because of that, let's assume that w of x comma y is only function of x, only function of x. So what happens if it is only function of x? So what will happen here is that this, I'm going to write here w of x, and here is a function of x, and here is w of x, and here is w of x. It is only function of x. It's no longer function of two variables. All right. Okay. So what happens to this equation now? What happens here is that this is equal to 0, because it is the partial respect to y of something that is only function of x. So that is obviously equal to 0. So what is left is just this, w of x partial of m respect to y equal to w of x partial of m respect to x plus n. And here what happens is that instead of being partial derivative, now it is normal derivative with respect to x, because it is only function of one variable. In functions of one variable there is no partial derivatives. Okay, so let's resolve this, because it is now a normal derivative, then we can solve it. Let's pass this to the other side. So what happens is that the n derivative of w of x with respect to x is equal to this to the other side, is going to be w of x times, I'm going to factorize here, is going to be the partial of m with respect to y minus the partial of n with respect to x. And just pass this to the other side and make the factorization. All right. So now what happens here is that you have a variable separable differential equation on w of x. All right. So let me write it. Variable separable differential equation. Okay. So what happens here is that I'm going to separate the variables. So continuing here is differential of w of x divided by w of x, because this goes as a division, the differential of x goes as a multiplication, and the n goes as a division, equal to the partial of m respect to y minus the partial of m respect to x, differential of x over n. Okay, so what is next is take the integrals on both sides, because it's a variable separable differential equation. So the integral of this is the natural lorem of w of x, and that is equal to the integral of the partial of m respect to y minus the partial of m respect to x over n differential of x. Now, okay, to clear the w of x, which is the thing we are looking for, is we are going to take the exponentials on both sides. Alright? So what is the value of w of x? The value of w of x is equal to an exponential of the integral of the partial of m respect to y minus the partial of n respect to x over n differential of x. Alright? Now this is the formula to find an integrand factor such that the cross partial derivatives will be equal, and then it will be now an exact differential equation. However, with one restriction. Now check this out. On this, the n is a function of two variables, and the partials are functions of two variables. But here the integral is normal integral. Normal integral. So that means that this formula works only if that is function of x. So that is the restriction, engineers. So you can use this formula to make it exact, as long as this is only function of x. If you find that this is not function of x, then you cannot use this formula, right? Okay, on the next video, I'm going to repeat the same process, but instead of assuming that w of x comma y is a function of x, let's assume that it's only function of y. and then you are going to get a very similar formula, but as a function of y. So you have two options. You can use this formula or you can use the other formula and the same restriction. Okay, now remember, because this cannot be 0. Why this cannot be 0? Because they are supposed to be different. Partial of m respect to y and the partial of m respect to x. Because they are different, then this cannot be 0. And because this is not 0, then there must be a value of w of x. Alright? Okay, next video I'm going to do the same process, but assuming w of y.